I wanted to give a quick summary of what we did in class today and tell you where we're headed next week. Today we played around with springs. And what we found when we played around with springs was that if we take a spring and we put a mass on that spring, then depending upon how heavy the mass is, that spring is going to displace by a certain amount. We'll call that a certain amount delta x. And what we found through experimenting today was that the force that we have to put onto that spring is actually proportional to the displacement x that we have from 0. Notice that I used delta x here, but this is really because my coordinate x is there and 0 is the equilibrium position of the spring. Now, there was one more thing that we did, and that was to account for direction. Because when I pull my spring down like this, the spring is now going to pull upwards. So the direction of the force that we have applied to the spring, the direction of the displacement that we have for the spring is downwards, but the direction that the force that the spring exerts is upwards. And so we use a negative sign for that direction. This relationship between force and displacement is called Hooke's law. And the K found in there is called the spring constant. And when we call it the spring constant, it is constant for a particular spring. But each spring has its own constant. In fact, the stiffer the spring is, the larger that constant will be. And so it measures the stiffness of the spring. There's a little bit more I could say about that spring constant here. Let's actually check out the units on it. Let's take a typical spring and apply a force of 50 newtons to a spring, and as a result, it stretches by a distance of, let's say, 1 millimeter. Now we want to know, what is the force constant? Or the spring constant? K for the spring. Notice I use these two words interchangeably, or two phrases interchangeably, the force constant and the spring constant. They mean the same thing, and they both refer to that constant K found in Hooke's law. So we're going to set it up like this. We're going to say that using Hooke's law, that the force that the spring exerts is equal to negative kx, which means that's the force the spring exerts, which means that the force that I have to apply to it will be the opposite of that. It will be equal to positive kx. Let's check a diagram so we can see what's going on. If we've got some object attached now, and if I want the spring to stretch to the right, I've got to pull it to the right, and that's our applied force. Meanwhile, the spring is going to resist me by pulling back to the left. So the spring force and the applied force have to be equal, have to be in opposite directions, but they will be equal so long as I'm stretching it slowly at constant speed. So since the force applied is kx and we have 50 newtons, and we have here 1 millimeter, I could use 1 millimeter, or I could write it in terms of meters. And if I do that, then I get K is equal to 50,000 newtons per meter. And what this constant tells me is that for this particular spring, if I apply a 50,000 Newton force to it, I will be able to stretch it by 1 meter. Most springs actually don't like that if you stretch them out 1 meter, because they go past their elastic point and they become permanently deformed. Think about a slinky. If you stretch it too much, you're going to deform it and it's not going to go back. Also notice that the units for K, the spring constant, which are newtons per meter, are not Newton meters, which are joules. The spring constant is not measuring energy, it's measuring a rate. It's the rate at which our force increases as the displacement increases. Well, I hope that is helpful to you, and I will see you on Monday.